So, good afternoon, ladies and gentlemen. We are happy to have Raffaele Grande as a speaker today. So, Raffaele got his PhD at the University of Cardiff, and then he was research associate with the University of Cardiff and also the Bristol University in the UK. Now he is with our institute. He won a postdoc position there last year. So the abbreviation here is the Institute of Information Theory and Automation. And he is an expert in curvature flow, and also now he's also getting into calculus of variations, I would say, as a real Italian. And today he will speak about stochastic control problems in evolution by horizontal curvature flow.
Thank you. I would like to thank you, Martin, for the nice presentation, and the title of this seminar is called Stochastic Control Problems and Evolution by Horizontal Curvature Flow. Practically, I put in connection two different topics, two different parts of maths. The stochastic optimal control on a side, and the evolution by horizontal curvature flow on the other. That is practically an evolution in a Sub-Riemannian setting. I give a short outline about this talk. I will start talking about Sub-Riemannian geometries. Then I will introduce what is the mean curvature flow, and then what is also the horizontal curvature flow. Then I will give a stochastic representation of this problem that was given in Euclidean setting by Cartelleghe-Butane and Campois, and in Sub-Riemannian 1 by Dragoni and Fornes. Then I will introduce some results that I obtained in collaboration with Nicolas Dier and Federica Dragoni about the P-optimal controls in the Heisenberg group, and a convergence result related to a particular kind of Sub-Riemannian geometries called Carnot group. Why is it so interesting to study this kind of problem? Because there are some application in neurogeometry, and also to have to reconstruct some images. Okay, image that you take a picture, then for a reason this picture is not complete, so you take like a photo. The photo is missing some details, but you can also think about a medical exam that can happen. So you want to know what is likely in this blind spot. So you can use this kind of horizontal mean curvature flow to reconstruct like an image. This gives you the advantage with respect to, as example, a neural network, that you don't have like the black box that you don't know what you are doing. Okay, let's consider M as a manifold, H sub-bundle of Tm called distribution of this bundle, and G a Riemann metric defining of this sub-bundle, which is roughly speaking a generalization of the inner product. So Sub-Riemannian geometry is the triple M, H, and G. I give you immediately an example, but it's the simplest one. So let us consider M equal the usual R3. Then we consider the vector fields 1, 0 minus x2 divided 2, and x2, 0, 1, x 0, 1, x1 divided 2. Then we use the assumption that we defined a metric such that x1 and x2 are orthonormal between each other. This describe implicitly, it's possible to write also the explicit metric, the Heisenberg group. That is the simplest case of Sub-Riemannian geometry that you can deal with. Then, of course, there is a condition. In practically, you can compute the commutator between x1 and x2, and you obtain a third vector field 0, 0, minus 1. This is so you can recover, starting from these two vector fields, a third vector fields that gives you all the tangent space for every point. This is called Ormander condition. This is something that often is applied in this kind of geometry. Then let us consider M, H, and G as sub-Riemannian geometry, and let us consider gamma an absolutely continuous curve, which roughly speaking, yeah.
Just to understand it, so at which point you have those two vectors, those give you the tangent space,
Yeah.
which somehow gives you locally the submanifold.
No, okay, no. The manifold is already defined. Yes, no, you can recover the third one using the commutator. So you apply the usual definition of commutator, and you apply the third vector field. That gives you the Watt tangent space. Is a weak condition of regularity of this kind of geometries. And then the main point of this kind of geometry is that not all the curves are admissible or horizontal, depending if we are in a setting of control theory or law geometry. So we can consider gamma an absolutely continuous curve. That means that is, roughly speaking, differentiable almost everywhere. And then we obtain that the gamma is an horizontal curve if it holds the following condition. That means that the velocity vector belongs for almost every t small to the space generated by the distributional point gamma t. And then we can define the following matrix sigma, putting all the vector fields all in columns. In this way, it's possible also to generalize the idea of gradient, Hessian, divergence, and Laplacian. Roughly speaking, what we do, we take, rather than the partial derivatives, we take the derivatives with respect to the vector fields, x1, x2, and so on. This is in a general setting, but we can write them in the Heisenberg group like x1 u, x2 u. The interesting thing is that when you compute the Hessian in this setting, the Hessian has not only second order derivative, but also first order derivative, which makes the problem when you deal with a partial differential equation much more difficult to deal with. And that's something that we have to consider in some setting. Okay, now I want to recover all the possible curves in this manifold. So what I have to do? The idea is to use in some sense an approximation. So we can say the vector field x1, x2 in the Heisenberg group. Yeah.
I'm just imagining.
Ah, okay, sorry. You were asking. Sorry. And practically you put like a third vector field 0, 0 epsilon, and then in this way you can obtain in R3 a Riemannian geometry. But when this epsilon runs to 0, you return back to the sub-Riemannian one. So using this 0, 0 epsilon, the admissible curves are all the possible curves like a classical Riemannian geometry. But if this epsilon runs to 0, you return back to the sub-Riemannian one. And so this is called the Riemannian approximation. That can be generalized also for more complex sub-Riemannian geometries. Then it's possible also to see that we have to adapt the definition of horizontal, of the normal, Euclidean normal. So we can take gamma in hypersurface in Rn, and then NE, the usual Euclidean normal. Then we define the horizontal normal like the normalized projection of the Euclidean normal on our distribution, and the horizontal mean curvature like the horizontal divergence of the horizontal normal. And I want to remark, I will sketch an example soon, that is not compulsory that if the Euclidean normal does exist, that this implies that also the horizontal normal exists. And this kind of points are called characteristics. Okay, I show with a small example. Practically, if you take a sphere, I consider the north pole of the sphere. This is our Euclidean normal. This is the space generated by the distribution, so it's the usual 1, 0, 0, 0, 1, 0. So it's the classical tangent plane. And then what happens? Happens that the projection of this horizontal normal is practically at all. So at that point, you cannot define the horizontal normal or also the horizontal mean curvature. So you have to deal with this point that does not allow us to define the practically neither the definition of Euclidean horizontal mean curvature. To avoid this problem, what we do? We introduce this third vector field. I wrote it for the Heisenberg group, but it's possible to extend, of course, with M vector field and N minus M vector field with approximate, which depends on epsilon. So we can extend the definition of horizontal normal like an approximated Riemannian normal, and we can extend the definition of horizontal mean curvature to an approximated Riemannian mean curvature. In this setting, the only remark that I have to do is that the characteristic point does not exist. Now, I will introduce what is effectively the mean curvature flow. I will start with the Euclidean setting, and then I will go in the sub-Riemannian one. So let us consider a family of smooth hypersurface in a Euclidean setting. Then we consider ME, the usual Euclidean normal at point X. Then also the Euclidean mean curvature KE, that is the divergence of the Euclidean normal. Then we say that gamma c is an evolution by mean curvature flow of gamma 0 if we start from gamma equal gamma 0 at time t, and then considering a smooth curve 0t which runs from 0t to Rn on this surface, it holds the following evolution. The following evolution, that means that the tangent velocity is equal to minus the mean curvature, representing in some sense that you can take this hypersurface, and that hypersurface shrinks in the direction of the Euclidean normal with a velocity proportional to its mean curvature. As example, if you take a plane and the plane does not evolve because the mean curvature is equal to 0. But if you take a sphere, the sphere you have to make that shrinks to a point. If you take a cylinder, the cylinder can be seen like F1 times R2 or a segment of R2. So it shrinks like until we obtain a straight line, and so on. So, however, this mean curvature flow represent this kind of evolution of this hypersurface. But there is a problem that was found by Evans and Struik. If you take a dumbbell, that is something hypersurface in this form, you can imagine that practically start from dumbbell like that. And then at a certain point, the dumbbell develops a singularity in this point. It's possible to see this. And then split up into different connected parts. And so the topological property of this upper surface practically changes completely. You obtain like two connected parts which are homomorphic to a sphere, and then they shrinks also into different points. So you have to pay attention to work with this kind of problem. So what we have to do, how we can approach this kind of problem? We can take, use a so-called level set approach, in which we consider U as smooth function which represent like a level set uxt equals 0, this equation, and then when you make the explicit computation, you obtain an equation in this form. Then the idea to approach this kind of equation differs from, there are two different ways to approach, but in some sense they are equivalent between each other. So you can regularize the function here, putting a plus delta. You find the solution for a plus delta for this equation that is regularized in some sense, and then you take this delta to 0. Or you work using viscosity solution and upper and lower envelopes. You work in both cases with a viscosity solution, but in one case you use a regularization. In the other case, you don't use regularization, you use upper and lower envelopes. So you use the nearest, in some sense, the nearest function from above and from below, which are continuous. Then can be, of course, generalized this kind of equation from a Euclidean setting to a sub-Riemannian one. But in this case, we have not only the difficulty related to the singularity, we have also the difficulty related to the geometry. So we have two difficulties. One, that the geometry is not so regular. And then there is also this kind of problem related to the structure itself of the equation. So you have, roughly speaking, use a double approximation, because while you do like a regularization or working with envelopes, then you have to put also some more approximation to recover the structure, not like in sub-Riemannian setting, but in Riemannian setting. So is a double approximation, and is very challenging, this thing to approach. Then we can repeat the same computation here, and we obtain a similar, in some sense, partial differential equation. But I want to remark that here we have not only first order derivative, but also the second order derivative, but also first order derivatives. So the Hessians start to be much more complicated to deal with. Then, okay, I introduced the approach related to PDEs. There is also another approach that sees this problem like a problem of reachability in a stochastic setting. So we can consider G, which goes from Rn to R, bounded uniformly continuous function. Then we can take T, strictly bigger than 0 fixed, and then we can define the following function Vtx. That is considered like an infimum of a class of some function, which are projection metrics, roughly speaking, with the following stochastic dynamic. Here, Bn, it represents the n-dimensional Brownian motion. Here is our class of A, so it's a class of symmetric matrices, roughly speaking, that are semi-positive defined, such that En minus nu elevated to the second is semi-positive defined, and the trace of this difference is equal to 1. And then it's possible to prove that V is a viscous solution of the following equation, which represents the Euclidean mean curvature flow. Furthermore, V is also continuous function. Then this theorem of characteristic dynamic in camp 1 and independently Sonner and Tozzi obtain the same theorem was generalized by Beer, Dragon, and Fornes in a sub-Riemannian setting. There are some few changes, but the most important changes is that there is a change of differential. While in the previous case we use an Ito integral, an Ito definition of stochastic integral. Here, due to the fact that we are working with Hessian that has first order derivative and second order derivative, we obtain that we have to use a Stratonovic integral. That is something a bit more technical in some sense. Then we have to put some condition about the metrics that are important, like that it respects the Riemann condition. So you have to take the commutator vector fields and find that for every point it's possible to generate the wall tangent space. And then there are some technical assumptions about the coefficient of sigma and of these covariant derivatives. So I give a short outline about these results of existence. The Euclidean case was proved by Evanson's proof in 1991 and independently by Ken Gigagoto with the two different approaches, one regularization, one upper and lower envelope. Then there is the stochastic approach that was given by Raffaele, and Sonner and Tozzi, one in 2001 and the other one in 2002. Then it was generalized also by the Dragon and Fornes in sub-Riemannian case, and then I generalize this case for the Riemannian approach, for the Riemannian approximation. In this case, we have something more because we know that it holds the comparison principle, something that we don't know in sub-Riemannian setting. We have to, however, work in cases that we know that there exists a comparison principle. In Riemannian approximation, we know that there exists, so the solution is unique and far more regular. So in Heisenberg group, however, there is a very nice property that allows us to simplify the problem, the stochastic dynamics passing through from the Ito integral to the Stratonovic one. The Hessian has only second order derivative, like the Euclidean case. It's possible to prove it doing the computation, and we obtain that the stochastic control problem for the horizontal mean curvature flow is given by the following stochastic dynamics, where V2 is the two-dimensional Brownian motion, and the controls respect the property that we've seen in the previous theorem. There are 2 times 2 symmetric matrices with the following property, and they are the set of the matrices that respect this optimal this condition admissible control. In the same way, it's possible to generalize in 3 dimensions. We obtain a similar result, and so it's simply a bit of there is a change about the structure. Here we have a what happened? Sorry, may you? I don't know what happened.
Control L.
Control L. Control L. Thank you. Here, of course, we have to take into account also the structure of the geometry. That is also this matrix. Then it's possible to generalize the structure given by Raffaele in sub-Riemannian setting. So we can take like the stochastic representation of the solution of horizontal curvature flow like an infimum of on a particular set of classes of control of an essential supremum of a function U. This function U0 can be smooth, Lipschitz, it depends on the kind of problem that we are dealing with. But we are taking like a function which goes from Rn to R. And then we can extend also the stochastic representation for approximating curvature flow in the following way. So we can obtain a V and B epsilon. The problem of this kind of solution is that they are not easy to deal with, because we have this essential supremum that is not so pretty technical to deal with it. So to simplify the problem, we introduce the P approximation that works exactly like P norm. So we can define Vp and V epsilon P in the following way. So we pass it from like an infinite norm, because morally there's a value function represent an L infinite norm, to a LP norm in a stochastic setting, and it's possible to prove that Vp for P which runs to infinity goes to pointwise, and the same taking epsilon fixed, Vp epsilon for P which runs to infinity goes to P epsilon. Furthermore, we have that Vp solves the following partial differential equation that is related to an approximative problem. And we remark also that we can write the P Hamiltonian in the following way. But here, as you can notice, there is a problem, because we have this P minus 1, minus P minus 1. So when P runs to infinity, then we have that this HP as function go to minus infinity. So we have to consider this trace as more as possible in some sense, in order to overweight this term. Okay, the optimal control, since it's a problem of optimal control, in the limit case, was proven by Dieter Koenig-Ness, is given by the following control function. So we can take at non-characteristic point the identity matrix minus the horizontal norm tensor product itself, and is the optimal control for this setting. And at characteristic point, we can take every admissible control, and it is optimal. So we have like a vortex of optimal control in some sense. So now we are asking how close we are is the P optimal control with respect to the limit problem 1. So it's a question that is important, because we are working with an approximation of V, that is P, and this gives us information about the structure of the problem. The first remark that we can do is that the optimal controls for P can be found not looking the value function, but looking for the supremum of HP. First of all, and secondly, that we can define all the admissible controls in the following way, which gives us the idea to, okay, we can start taking a control. We know that we start with a vector of length 1. We can rotate this vector in a 2 times 2 of a 2 times 2 matrix, and then we obtain all the possible admissible control. So this leads to the following theorem. So we can consider HP like in 17, that is this one. sorry. Then fix the R and the Q, which belongs to R2. We can consider M like a diagonal matrix without loss of generality. And then for a large P is an asymptotic result, it's not for all P, so P has to be very big. We obtain that the optimal control can be expressed in the following way, using a standard rotation matrix with an angle in the form theta bar equals C times 1 over P plus a no of E divided P elevated to the second, where C is a constant depending on R, Q, and M. Q and M represent the horizontal gradient and the horizontal Hessian, morally. To prove it, what we do? Okay, the proof is something works like that. So we can take, we represent the vector that generates the optimal control in the following form, because it has to be of length 1, so we can represent it like cosine alpha, sine alpha. Then we rotate it, obtaining all the possible admissible control. Then we write the P Hamiltonian, making all the computation, obtaining in this way, rather than a problem of finding the solution for variables, only one. And then we can derive this function with respect to theta, and then we can use the following ansatz. And by using the Taylor expansion of sine and cosine, we can solve the linearized problem. At the characteristic point, the situation is much simpler because we have that this Q here at the characteristic point can be represented by a null vector 0, 0. So the whole this part disappears. So we have only the trace of this matrix. And we record that we can have that all the admissible controls are also optimal. So it leads to a new theorem. So we can consider a P Hamiltonian as introduced in 21. That means that one. Then we can prove that the optimal angle depends practically on the difference between lambda 1 and lambda 2. If it's positive, theta bar is pi divided 2. If theta bar is equal to 0, if lambda 1 minus lambda 2 is negative, and whatever theta we choose is fine if lambda 1 is equal to lambda 2. This is the case as example of a sphere. So I will give a sketch of the proof. So we can start, since every optimal control is admissible, we can start from that one, 1, 0, without loss of generality. We rotate it, we put this omega theta in HP, and then we compute the first derivative in order to obtain the critical point, and the second one find effectively the maximum. So it's a very straightforward proof in that sense. Then here there are some numerical simulations in which here we consider our angle theta. Here we consider the length of our horizontal gradient morally, and here the value of the function of the P Hamiltonian associated. We make some simulation with P equal 10, lambda 1 equal 1, lambda 2 equal 0, and R equal 1. And we notice that for alpha equals 0, the set of the optimal value is discontinuous because due to the structure of our P Hamiltonian, we obtain that the optimal is obtained in 0 and pi divided 2, while for alpha equal pi divided 4 is, I don't know if you see it, like a continuous continuous set like that, in some sense. We did also some numerical simulation about the direction of the optimal control. We always take p equal 10, lambda 1 equal 1, lambda 2 equal 0, r equal 1, and we notice that here there is like a vortex discontinuity where does not hold our asymptotic expansion, and we need also some numerical simulation with the sphere. Here is particularly clear what is happening when you say that every optimal or every admissible control is also optimal. You obtain something like a vortex. So when you see something, I mean, when you have practically that you are in a artistic point, then you obtain that all the possible direction gives you an optimal control, and so it represented here in this way. Then the major question that I wanted to approach here is related also to this theorem. So let us consider some assumption on sigma, like that is globally Lipschitz and bounded. Then, for sake of simplicity, we consider this drift term equal to 0. Then we consider U0 a Lipschitz continuous function, and Vp epsilon as defined as before. Then, considering this epsilon in this form, we have the following inequality. This is a work in progress. We are finishing some estimates in some direction, while the mean soup inequality is already given, is already good. And to prove this convergence result, what we have to do? We divide this problem into different sub-problems. One estimate like a MIF, and the other estimate like a limb soup. The case of limb soup is simpler to approach because we have only to extend the class, because we are working like with matrix m times m. It's possible to extend this kind of matrix, especially in the group line. We start from a 2 times 2 matrix, like this one is optimal, then we can extend them like 0, 0, 1. And we obtain the admissible setting, the admissible control for the other the other side, while the other direction is more complicated. Then, for the case of limit, we need to work on epsilon p optimal control problem. We start making some estimate related to this quantity, using some hypothesis, like, for example, that U0 is Lipschitz. Then, using the Minkowski inequality and the assumption that the function of U0 is globally Lipschitz, we can obtain that we can move from a problem of differences between value function to a problem between trajectories. So we have to understand how much the trajectories of the stochastic dynamics are near to each other. Then we apply the Ito's lemma for the LP norm, because we can recover it in some sense to some computation. Then there are some simplifications that are related to the structure of the problem. As example, the expectation of an Ito integral is equal to 0. Then, making some estimate, we can recover something in a form in which it is possible to apply the Brown-Wann's lemma. We use, as example, Young's inequality and so on. And then, using a particular choice of epsilon, we obtain that there exists the convergence. So there is the limit norm, the lim sup norm, and then we obtain what we are expecting. Okay.
Okay, thank you very much.